Well, good day, everyone. This is Chris back again with the Ancient Scholar, and this is a video 2 in a series of videos on. I basically posed the question: why is glass transparent to light? And in the last video, I told you a little anecdote about Richard Feynman, Dr. Feynman, and that led us into a discussion or into another question. Where in fact glass is not transparent to every type of light, only certain types of light. So, to understand this, we need to we don't really need to understand quantum mechanics, at least not the formalism, the mathematics, but we do need to realize that this is a that we need to invoke quantum mechanics to actually recognize or realize what's going on. Well, if you remember from my light videos, I had talked a little bit about light, and I said, hey, look, let's say that I have an atom. We'll just say a hydrogen atom, okay? I have the nucleus, and then I have the electron in a certain energy level. Again, electrons don't literally orbit, but let's just say, for the sake of this video, for the sake of simplicity, that I have an electron in a certain level of energy, and let's say that electron is at its ground state. At its ground state. Okay. In this case, it would be n equals 1. It's a ground state. Now we also know that electron could exist in a higher energy state. So I'll draw another state of energy up here, higher, a little further away from the nucleus. We would call that n equals 2, or we would also call that the first excited state. The first excited state. Okay? Now we know one way of getting the electron from the ground state to the first excited state is if we had a photon of light were to come in and hit that electron and give that electron its energy. The photon of light basically is absorbed. It basically just goes away, gives all of its energy to the electron, and allows the electron to get up to n equals 2. Well, we know that photon, the energy of that photon, has to be exactly the amount of energy needed to get the electron from the ground state to the first excited state, second, third, whatever. Whatever that energy is, that photon needs to provide the exact amount of energy. If that photon only has half the amount of energy, we'll say, required to get the electron from n equals 1, n equals 2, guess what? That electron ain't going. It is not going. The photon has to have exactly the proper amount of energy, because if you remember from some of the quantum mechanics we talked about, the electron, it cannot exist here, right? It can either exist in n equals 1 or n equals 2 state. There's no half butting it as far as electrons. It's all or nothing as far as an electron goes. It's either here or it's there. It either has enough energy to get up here, or it ain't moving. It ain't budging. It is going to stay down there. That light, then, if the light didn't have enough energy to get the electron from n equals 1 to n equals 2, well, what would happen? Well, that light would just go right on through the atom, wouldn't really interact with it at all, right? It basically, the atom wouldn't really care about that light. It only cares about that light if the light actually has enough energy to get the electron to higher energy levels, or allowed energy levels, but no half-arsing it. No half-arsing it here. Okay, so if you understand that, that should lead us in to what's to come. Well, when we have something like glass, or some sort of solid, we'll just say solid, we'll try to keep this simple. When we have some sort of solid, I'm not talking about just a single atom. I'm talking about a very specific arrangement of atoms. And, generally we can have two different types of arrangements. We can have what's known as a crystal, and a crystal is a very orderly very orderly, very concise arrangement of atoms. Very orderly, very concise, it repeats, there's symmetry, so on and so forth. That's the definition of a crystal. I can also have something that isn't particularly orderly, it isn't particularly concise, and it's non-repeating, and lo and behold, we actually call that a glass, believe it or not. So we can have metallic glass, and we can have the glass that you and I are aware of. Glass needn't be transparent to visible light. If you take obsidian, for example, obsidian is black in color. It's certainly not transparent, but it's still a glass because it's a solid that doesn't meet the definition of a crystal, where I have very orderly, very concise, repeating structure. And that's really all the depth I'm going to go in there, into the different types of solids. But be that as it may, in a solid, instead of just having a single atom of hydrogen, for example, floating around in its gaseous state, I have an arrangement. I have an arrangement. I have a large arrangement of atoms. Okay, so what do we have going on here? Well, when we talk about the quantum mechanics, specifically when we talk about maybe the Schrodinger equation, which is really good when I take a hydrogen atom all by itself, or a one electron atom, the Schrodinger equation, pretty much 100% accurate and precise with its predictions. When I start throwing more electrons into the mix, not so much, because I have electron-electron repulsion and attraction, and things just get a bit too messy for us to calculate. So we have to do approximation techniques. We have to basically approximate a little bit on the Schrodinger equation, and through the approximations, we can come up with predictions that are pretty accurate. Well, if I have millions and billions of atoms and electrons all kind of combined together in a solid, do you think I have a very good framework for calculating all this stuff that's going on? And the answer is not really. We have to do some really good approximating here. But what we can say for the most part is, if I have lots and lots and lots of atoms, and be it a glass or a crystalline structure, I have lots and lots and lots of quantum states, okay? Different quantum states with lots and lots and lots and lots of quantum numbers, lots of n's, lots of l's, lots of m's, and obviously, spins. I can only have two types of spin with electrons, but I have lots of different states. Because these atoms are so close together, there's lots of electron-electron interaction, there's repulsion, there's attraction, there's a whole lot of stuff going on. We don't necessarily have just a single level of energy or state or what have you. We have lots of states. So if you can imagine that this, on the y-axis, I'm going to plot energy here. Imagine that this is energy, and I have whatever kind of solid. Doesn't really matter at this point. And I have lots and lots of atoms together. I have lots and lots and lots of states here, okay, that the electrons can be in. And I'll just put in little dots here that the electrons are in all these different states. They fill up, according to the Aufbau principle. The Pauli exclusion principle still applies. You can't have an electron with the same quantum numbers and all that, so we have to have lots of different states, and the electrons can exist in those states. And just like how the hydrogen atom was quantized, or had very discrete levels of energy, the energy levels are discrete here as well. And then I may have another chunk, maybe at a higher energy level here, of open quantum states that electrons could be in. Well, maybe this other level of quantum states is, well, it will be at higher energy, right? Where do the electrons like to go? Where do they like to be? Well, they generally like to be down here at lower energy levels, right? Now, we could make them go to these high energy states, but let's just say that we have this for now, just to kind of get the general intuition going. So this is an arrangement of some solid. We don't know what kind of solid, but it's just some solid right now. Okay? My electron's down here, and we need to realize that this little gap here, just like in the hydrogen atom, from the n equals 1 to n equals 2, I can't have anything in between. Electrons, they don't go in between. So this is kind of a forbidden zone. Okay? Forbidden zone. Electrons cannot exist here. There are no quantum states for electrons. They can be here, and they can exist in quantum states here, but they can't be here. So to get an electron from here and to promote it to here, I need the exact amount of energy to get through this gap here, right? Whatever this energy is, and we don't know, it could be any arbitrary value that we can make, that you want to make up for now. But to get an electron from down here to up here, I need to hit the electron with a certain amount of energy to overcome the energy of the gap. Now, if I only give it enough energy to go halfway through the gap, well, the electron isn't going to go up halfway and stay there, right? The electron is just going to stay right down there and go, hey, sorry for you, mate. I'm not going anywhere. So that's the first big point here. Lots of quantum states here, and we actually call these areas bands. Bands of energy, right? Because I have several bands here, but I don't have any in the forbidden zone. This down here is generally what we call the valence band. Okay, that's the valence band down there, because I'm going to have a lot of valence electrons here. And this band up here is commonly called the conduction band. Conduction band. And we know that conduction refers to the movement of electricity, right? Electricity conducts or it moves. Well, what is electricity? Conduction is nothing more than the movement of electrons. So that would make sense to call this conduction, because if I can get an electron up here, if I can move an electron up here by giving it enough energy to get through this gap here, then it conducts, right? It moves, it conducts. So I think I'm going to go ahead and just cut it off here. I think we have a fairly decent framework, that we have these energy bands and that we have these gaps in these bands, and I need a very specific amount of energy, and it varies from substance to substance, but I need a very specific amount of energy to get the electron, to promote it through this gap, to get it up into these other quantum states up here in the conduction band. Okay, guys, as always, thanks for hanging in there.